Hello, Math 30-1 students. We're looking at lesson 8.1, Understanding Logs. We're going to do a recap from our lesson 7.3, which is the common base method, just before we continue. So first of all, we want to get them to be the same bases, the 4 and the 8. So we're going to write them both as 2 to the power. So 2 to the power of 3 replaces 8, and then we leave the power as it is outside of the bracket. On the other side, instead of 4, we write 2 to the power of 2. And then x minus 9 stays outside of the power. Now, whenever you have a power raised to a new power, you actually have to multiply them together. And in this case, we're going to have to distribute. So you're going to have 2 to the power of 9x plus 12 is equal to 2 to the power of 2x minus 18. When you get the same bases on each side, and there's only one of them, you can actually cross them off, leaving you with the powers equaling each other. So what we're going to do is bring the x's to one side. So 9x, we're going to subtract 2x because we have to isolate for x. And then negative 12 minus 18 is going on the right side. So 9x minus 2x is 7x. And negative 12 minus 18 is negative 30. So we're going to divide both sides by 7, which means that our solution is x equals negative 30 over 7. So we'll leave it like that. So for this lesson, what we're going to do is be looking at the exponential function y equals c of x, and we're going to look at the inverse of it. Okay, so if we were to swap out our x and y and solve for the other one, there's a step that happens in order to solve for your y value, and that becomes making it a log function. So I'm going to show you how to transfer one form to the other form. So this is actually on your formula sheet, which is nice. You just need to practice how to actually do this. Okay, so what we need to know is that our power becomes our answer. Our base becomes this little mini number right here. So our base is that little small number, and our x always goes with the log value. Okay, so look at where the placement is. Now, whenever you don't see a base, when it comes to a log function, the base will always be 10. So if you don't see a number as a base, that means 10. So what they're showing you, for example, is if you see log 3, that actually means log base 10 of 3. Okay, so the base is 10 if you were to change this to exponential form. It's just so common that we don't have to write it. So it's just a way of writing less, because that 10 is the most common base that we will use. Example number 1. So they want us to evaluate this. So we can use our calculator. So I want to show you the steps in order to use your calculators, but then I want to show you another method as well. So there's 2 different calculators versions, depending on which version you have. If you have the newer version, you're going to be able to do it, I believe, in nope, not in this version. Oh, there it is. Okay, so if you have a newer version calculator, you're going to be able to do alpha window, and then you'll see this number 5. For you guys, you should see this log base. So what it should look like is this, where you're able to put that little miniature number in the first number right here. So it's going to be log of 2 and then 32. So if you have a new version calculator, you should be using alpha window. And I believe, I'm hoping it's the same for your calculator. It should be number 5. So alpha window number 5. Yep, I just checked. Now, if you have an older version calculator, you're going to have to do a few more steps. You're going to have to go to, let's see if I can find it. So if you have a newer version older version calculator, sorry, like the TI 83s, you're actually going to have to go log of the larger number, which is 32, and you're going to have to divide that answer by log of the little miniature number, which is 2. So log big divided by log little also gives you the same answer if you don't have this log base number. Okay, so this is just a way around it if you don't have that button. Okay, so those are the two methods. So as you can see, when I go alpha window for you guys number 5, you can put the 2 there and the 32 here, and then that gives you the answer of 5. So we know the answer is 5, but I want to show you different methods as well. So this is called the common base method when it comes to these ones. So common base method would be log of 2. You're going to change this 32 to also be a base of 2. So 2 to the power of 5 actually replaces 32. The reason that this is a nice method is because if you ever get these bases being the same, this crosses itself off, leaving you with the power as your final answer. So we know that the answer is 5, and there it is. It's in your power spot. So I'll show you that common base method with the next one, and I'll show you that you get the same answer with your calculator. So log base 9, we're going to write 81 as 9 to the power of something. So we're going to have the 5th root of 9 to the power of 2 is 81. And then we need to write this as a power instead. So whenever you have an index, that always goes and looks like this. So you still have this 9 to the power of 2, but outside you're going to always have the power at the top, which there isn't a power in this case. There isn't a bracket around it. And then you'll have the index goes at the bottom of the fraction. So that's a way of rewriting the 5th root. So you'd say to the power of 1 over 5. The reason we like to do that is because now we can multiply these powers together. So you're going to get log of base 9, and then 9 to the power of, whenever you multiply a whole number by a fraction, I like to put a 1 underneath it because the tops go together, the bottoms go together. So it'll be 2 over 5. Now these guys all cross off, leaving you with the answer 2 over 5. Now 2 divided by 5 is equal to 0.4, and I'm going to show you that you get the exact same answer if you were to do this with your graphing calculator. Okay, so newer version calculator, you can go alpha window, number 5. You're going to put that 9 in that little box spot. And then you're going to put the 5th root, so you're going to have to go 5 math, number 5. Okay, so the 5th root, and then in the underneath in the radicand, you're going to have 81. So you'll see that I get 0.4 as well. Okay, if you're doing it with the older version, the TI-83s, you're going to have to go log of the 5th root. So I'm going to have to put 5 and then the number. So I just have a different version graphing calculator than you do, but you're going to have to go and make it look like this. 5th root of 81. And then you're going to have to divide it by, outside the bracket though, log of 9. And you'll also get the same answer. So this is just using its newer version versus older version calculator. Our next one. Now the base, if you don't see it, is a 10. So what this really means is this. Okay, so we have log base 10 of 1 million. So what we can do is get common bases. Well, log of base 10, 1 million is the same as saying 10 to the power of 6. Now, since these two bases are now the same, they cancel it all out, leaving you with 6 to the power as your final answer. You can always put this in your graphing calculator. We have this nice button in our calculator on your actual screen. So if you guys look, it's like wherever you see that letter N, there's a log, L-O-G. So you can press log, and whenever the base is 10, you don't have to write it. So you can just go log of 1 million. And you'll get 6. Our next one, we have log base 3. We're going to write 3 to the power of 2 multiplied by 3 to the power of 1/2. Now we're going to need to multiply these guys together. Actually, with our rules, if you guys remember, whenever you have two bases multiplying, we're actually going to have to add the powers, so m plus n. So it's going to be log of base 3. You're going to have to write it as 3 to the power of 2 plus 1/2. So we're going to have to add 2 plus 1/2. So 2 over 1 plus 1/2, we're going to have to get common denominators by multiplying this by 2 and this by 2. So that's 4 over 2 plus 1/2 equals 5 over 2. So we have log base 3 of 3 to the power of 5 over 2. These guys cross off, leaving you with the answer of 2.5, which is 5 over 2. So what we need to remember is that whenever you have a 1, it doesn't matter what the C value, as long as it's greater than 1 and not equal to, as long as it's greater than 0 and not equal to 1, this will always be true. So what we need to remember is that this is always equal to 0. The reason being is that, let's say we write it as c to the power of something. Well, c to the power of 0 equals 1. So we're replacing 1 with c to the power of 0, and your power is your answer. So 0 is your answer. Now, if you don't see a power, it's 1. So your answer in this case is 1 because the two bases of c would cross each other off. And then another cool thing, I'll just rewrite this so you guys can see this a little bit better. Whenever these bases are equal, like I said, the power is your answer, so x is your answer in this case. And then c to the power of log cx is actually equal to, do you guys see how this log of c, they both have the same bases? These guys would cross each other off, leaving you with the answer as x. So as long as x is greater than 0, this would actually work. Okay, so these are just kind of rules that we use when we're solving these. So these are kind of like fundamental, like will always occur. Determine the value of x. So we're going to actually work on solving. So we're going to use this inverse property and learning how to transfer it. So I'm gonna write this equation out here, right here, so you guys can see what it looks like and what I'm actually doing. So log base c of x equals y is the same as saying c to the power of y equals x. So what I like to do and what I find helps me in these kind of situations is I like to label everything. Well, I know that the 4 is c, the x is going to be x, and the -2 is y. So now I need to write it in the form c to the power of y equals x. Well, c is 4, y is -2, so you're going to write it as to the power of -2, and then your x is x. So that's all you're doing, is we're rewriting it into an exponential form, and then we can put it in our calculator and solve for it. So 4 to the power of -2 equals 0.0625, which we can change it to a fraction, so x is actually equal to 1 over 16 for the first one. B. Again, I like to label it 16 as c, your x stays the same, and this is your y. So we need to write it as c to the power of y equals x. Well, c is 16, our power is -1 over 4, and our value of x stays as x. Again, put that into your calculator. 16 to the power of, in brackets, -1 divided by 4 will equal 0.5. So x is equal to 0.5, which is 1 over 2. So 2 ways to write that. C. Log base x, I'm just going to rewrite this so I can label this clearly, but c is your x, so this is my x. This 9 is the x in the actual equation, so even though they use the same letters, like it might be in different order, so you still need to rewrite what's in the spot and not what's actually labeled a certain way, and this is your y. Your answer is always your y. So we need to write x to the power of 2 over 3 equals 9, because it's always c to the power of y equals x. Now we need to get rid of this. To move it to the other side, we would always have to take it to the power of the reciprocal. So if you ever want to get rid of a power, if you do the reciprocal of it, it will bring it to the other side. So instead of to the power of 2 over 3, we're going to take that to the power of 3 over 2. What you do to one side, do to the other. The reason is the 2's will cross each other off, the 3's will cross each other off, leaving you with x to the power of 9. X equals 9 to the power of 3 over 2. If you put that into your calculator, you should get 27 as your final answer. Okay, so that is how you transfer a logarithmic function into an exponential function. Okay, so whenever they ask you to write something as the inverse, they're just asking you to write it as a log function. So write it as a log function. That's pretty much what the question's saying. So first you need to label it. Well, we know that our equation always looks like, whenever it's in exponential form, it should be c to the power of y equals x. Okay, so that's what it really is. So when we're rewriting this, we're going to have to make sure we write log base c of x equals y. So log base, our base in this case, guys, is 1/2. Our x value is our answer, which is f of x. So we are going to leave it as x. And then our y value is our power, which is x as well. So up to you if we want to rewrite it like this. That would always work here. So you can leave it as x and y. It's just about rewriting it using the values. So I just kept y is what our answer was, and x within the log function, just to make it a little bit easier. Okay, so now that I've rewritten it, I want to sketch this graph. So I also want to sketch the original one and then compare them. So we're going to go over to Desmos just to get a clearer picture of what this all looks like. I find that the graphing calculator doesn't do the greatest job when it comes to graphing these guys. Okay, so we have y equals, in brackets, 1 divided by 2 to the power of x. There you go. Okay, so this is our typical kind of exponential function. This is a decreasing exponential model. And then if we were to graph the other one, y equals log, there it is. Log, we're going to have to put the base I'm going to have to do it in the other manner because it's not really showing it to me like this. So I'm going to do it in that method where I have to take the older style calculators, where you always have to take log of your big value divided by log of your little number. Oh, there is a base one actually. Okay, let's clear that again. Okay, I just found the button. So in my functions, I have this log of a value, so I can actually rewrite it there. Grr. Okay, let's try this one more time. If not, I'll go back to the graphing calculator. Okay, it's not working here. Okay, so let's go to the graphing calculator. I was trying there and it wasn't letting me write in the base nicely, so I've decided to go back here. And then our log function, log. Now, if you have the older style calculator, you're going to do log of x divided by log of 1/2. Okay, so that would be one way to write it. And then you'll get something like this. If you look at it, it does look like a reflection along your y equals x line. So that's what should happen because they are inverse functions of each other. The other way of writing it is in my y equals. I could have gone for the newer version calculators, alpha window number 5, and then rewritten it as your base is 1/2 and your value of your x is x. And you'll see that it just traces over the other one. It's going to look identical, okay? Okay, so it would be identical to that red one. So it will, if you guys do it on your calculators, it will trace over it. This one's just that version that doesn't do everything the exact same way as your calculators. So what we want to do is sketch this, sketch what this looks like, and then we are going to state the features, talk about what features are in common, what are they, what's different about them. Okay, so our exponential form, guys, if you're rewriting it, I'll do this one in one color. Okay, so there's one graph. Now, what is nice is I am going to find that there is a point of intersection here. If you guys look, there's a point that they match up to. So it's approximately there, but you could always find it by doing the intersection. So that would be, if you go second graph, you can use this graph to plot a few values. So there's different kinds of things you can do, but in the end, you just want to have a sketch of what that looks like. Okay, so with another color, I'm going to graph the other one. Okay, so they should be mirror kind of images of each other if you were to actually look at this a little carefully or draw it a little bit more accurately. So what we want to do is figure out the domain and range when we're comparing them. So let's talk about f of x versus its inverse. So f of x will be the graph of 1/2 to the power of x, and its inverse will be the log 1/2 of x graph. So domain. The domain of an exponential function should be, it should be going from -infinity to +infinity. Versus the logarithm, if you guys look at it, it should go from 0 and up. Like it shouldn't touch 0, it should be greater than 0 and up. So we should have rounded brackets at 0 and rounded brackets at +infinity. Okay, so you'll see that the green graph, it goes from 0, it looks like it goes very near to 0, but there's actually this vertical asymptote there. And then it's greater than 0, all the way up to +infinity. Then our range, you'll see that they switch features. So this one will have the same features, and then these guys will have the same features. So our range is going to be from 0 to infinity. And our range for the logarithmic function is going to be from -infinity to +infinity. So you should see that they switch features. Whatever's true for x becomes y, and whatever's true for y becomes x. So that's what always happens in inverse functions. The x-intercept, I'm going to find them for both, but for exponential functions, there are none. There's no x-intercepts in this case, versus if you guys look at the other one, you can find it by going second trace, go to number 2, 0, move your cursor to the left side of that x-intercept. I just have to get on there. Yeah, left side. and then move it to the right side of that x-intercept, and it should be at 1. So the coordinates would be at 1, 0, but we just want to write that the x-intercept equals 1. Y-intercept. The y-intercept will actually be at 1, and this one will have none. Again, do you guys see how these features switch? Because the x's becomes the y's and the y's become the x's. This is true for all inverses. And then asymptotes. For an exponential function, you should see that there's a horizontal asymptote at y equals 0. But for the logarithmic, you should see that there is a vertical asymptote at x equals 0. So again, those features switch. Example number 4, without using technology, evaluate the value of log base 3 of 50 to 1 decimal place. So a way of rewriting this would be going log of 50 divided by log of 3. So that's one way to do it. Or if you're trying to do this, guys, if you're trying to do this without a graphing calculator, it's kind of an estimation, like a trial and error kind of method. So you're saying log of 3, 3 to the power of what gets me as close as possible to replacing 50? Well, the two numbers that would surround 50, let's see, 3 to the power of, so we're just trying 3 to the power of something that gets me close to 50, close as 50 as I can. So I'm saying 3 to the power of, I'm trying to do like a few different values. So the two values that kind of surround it would be these two. They're not right on it, but they surround it. The reason being is that 3 to the power of 4 is equal to 81. 3 to the power of 3 is 27. And what we're saying is that we know that our value is going to be between, our answer is going to be between 3 and 4. Because if we can get the same bases, then they cross each other off, and we know that the answer is going to be between 3 and 4. It's kind of halfway, so if I were to guess, I'd say that the answer is either 3.5 or 3.6. The reason being is 50 is kind of in between these two numbers. Okay, it's almost symmetrically between those two numbers. So what you're trying to do is just figure out between 3 and 4, which is it closer to. So I found that it was about 3.5 or 3.6, but then you can always use your calculator to check, and the answer is 3.6. So this is just a strategy. You can always use your calculator, of course, for all these questions, but it's just a way of saying, does my answer make sense? Example number 5. So they're giving you this equation here. So we use logarithms when we're talking about earthquakes. So the Richter scale is using the m equals log of 1 value of A, which is the amplitude of the ground motion, versus the initial ground motion when an earthquake occurs. So in 1946, an earthquake struck Vancouver Island off the coast of British Columbia. It had an amplitude that was 10 to the power of 7.3 times A0. What was the earthquake's magnitude on the Richter scale? Okay, so what we're trying to do is we're just trying to replace, like, it's just saying it's this many times greater than that. So we're just trying to put it into the equation and see what we get. So we want to look at what it is on the actual Richter scale. So what's the magnitude? Pretty much is what we're saying. Okay, so when we put this equation in, we already know that we're comparing that 10 to the power of 7.3 to 1, because it's just saying that it's this many times greater than a value, and we're assuming that it's 1. So if I said something was 5 times greater than something else, we can say 1 versus 5. That would be a comparison. So we're replacing A with 10 to the power of 7.3. So the magnitude equals log of 10 to the power of 7.3 divided by 1. That's pretty much what we're really saying. Now the base, if you don't see it, is going to be 10. So for earthquakes, the base is 10. And then we have 10 to the power of 7.3. That common base method states that whenever the bases are the same, we can cross each other off, and the magnitude is 7.3. So the power is your answer. So we already know that on the Richter scale, we're going to be at a 7.3. Our next question is, the strongest recorded earthquake in Canada struck in off the coast of British Columbia in 1949. It has a Richter scale reading of 8.1. How many times as great as a 0 was its amplitude? So we know that that magnitude is 8.1. So we're kind of going in reverse. So we're going to say 8.1 equals log and then we're going to have our A, which is what we're trying to find, versus our A0 we're comparing to 1. So we're going to replace A0 with 1 again. So in order to do this, I'm going to change this to exponential form. So if you don't see a base, guys, it's 10, right? So we know that that is what we should label our C value as. Then we're just rewriting it into that form. I'm just going to write it again for you guys to see. But it's always C to the power of Y equals X, right? And then our log form, our answer is always our Y value. And this value right here is your X. So it's going to be 10 to the power of 8.1 equals our A over 1. The 1 doesn't affect our answer, so we don't need to even care about that. But this is it. This is going to be the amplitude. So we're going to just put 10 to the power of 8.1, which is a really large number. So if you guys look at it, it's like 125,892,541. So that would be our answer, but I'm going to leave it like this. So that is the actual amplitude of this earthquake. And now they want you to compare the seismic shaking of the earthquake that was the answer for B to the answer of A. Okay, so what we're doing is we're actually comparing them. So we already know that we always want to compare the amplitudes. Okay, so once you have these answers, so the answers that I'm talking about is this one here, and the original amplitude, that guy there. So if you actually divide them, that's how you can figure out how many times stronger one is versus the other. So a way of comparing them is taking 10 to the power of the higher one, which is 8.1, and dividing it by 10 to the power of 7.3. And whenever you divide bases that are the same, you can actually subtract the power. So 8.1 minus 7.3 gives me 10 to the power of 0.8. So if you put 10 to the power of 0.8 in your calculator, you get that the one earthquake that struck off the coast of British Columbia was 6.3 times stronger than the one that struck off of Vancouver Island. Okay. So B is 6.3 times stronger than the answer for A, is what I'm really finding. Our next question is the largest measured earthquake struck in Chile in 1960. It measured 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake than the 1949 Haiti Guay earthquake, which measured 8.1 on the Richter scale? So we're measuring two kinds of magnitudes, a 9.5 versus a 8.1. So a quick way to do this, guys, and a way that you can really simplify your work is you just have to always write your magnitudes as 10 to the power of the value that they're giving you. So if they're giving you the magnitude, you have to write 10 to the power of 9.5, and the other one would be the 10 to the power of 8.1. Whenever you want to compare them, take the higher one and divide it by the lower one. And then just like in the previous question, 10 to the power of 9.5 minus 8.1, you want to subtract the powers to simplify your bases. So 10 to the power of 9.5 minus 8.1 gives me 25 times larger. So we know that the Chile earthquake was 25 times stronger than the 8.1 earthquake. Okay, so the 9.5 magnitude is 25 times stronger than the one that is 8.1. Our next example is comparing sound. So it's very similar to what we just did. The only difference is we have this 10 in front that we're going to have to work with and deal with in order to solve anything. So example number 7, the loudness or intensity of sound can be measured in decibels. The intensity of two sounds can be compared using the following formulas, where I represents sound intensity and I0 represents the reference sound intensity, the threshold of hearing. So we want to determine the intensity of the threshold of pain of 125 decibels compared to I0. So we want to determine the intensity. So they're giving us the decibels. So we're going to have to go 125 is equal to 10 log of I over I0. So what we're trying to find is pretty much, what is this? So step 1, divide your decibels always by 10. So that's a little trick that you'll have to remember when it comes to sound. So 125 divided by 10 is 12.5, and that's equal to log of I over I0. Now to get this by itself, you're going to have to change it into exponential form. So it's always going to be the base to the power of your answer, which is 12.5, and that's equal to I versus I0. So if you put that in your calculator, 10 to the power of 12.5, you get this big number. That is the intensity. Okay, so this is our answer. Now we want to compare them. So we want to compare two decibel levels. And a trick to this is using the same thing we did before, but whenever we have decibels, we're going to have to divide those numbers by 10. So in the earthquakes, we just had to take 10 to the power of those numbers, no extra work. But here we're going to have to actually divide these numbers by 10 first. So that's going to be 6.7, and this one's going to equal 2.2. And then we're going to write them as 10 to the power of 2.2. That's the actual intensity level. And this one's going to be 10 to the power of 6.7. Once you have it as intensity, so this is one intensity, this is the other intensity, now you can divide them. Always the higher number divided by the lower number. So in your calculator, 10 to the power of 6.7 divided by 10 to the power of 2.2, and that gives you 31622 point, I would say 8. So we know that it's approximately 31,623 times stronger. So we know that a piano is 31,623 times stronger than a whisper. And that's it for lesson 8.2. So make sure you guys try the homework for this. Ask me questions if you're not getting it.